Discussing about the time period of a satellite. The time period of a satellite is defined as the time taken by the satellite to complete one revolution around the Earth. That means if we take a satellite of mass m that is orbiting around the Earth at an altitude h with an orbital velocity v, so we have to see what is the time taken by this satellite to complete one complete revolution. We will solve this by directly the time taken will be equal to the distance traveled divided by the speed. The distance traveled in one complete revolution is the circumference of the circle in which it is orbiting. It is orbiting in a circle of radius r, so the circumference is 2 pi small r and the velocity is d. So the ratio of the circumference of the circle in which it is orbiting to the orbital velocity of the satellite gives us the time period. So easy. So time period will be equal to t will be equal to 2 pi r, that is circumference of the circle in which it is orbiting, divided by orbital velocity v. Now we know that the orbital velocity is equal to r root g divided by r. Now putting the value of v here, we get t is equal to 2 pi r divided by r into root of r divided by g. This is simple calculation. Now the time period gives, taking r into the root, that gives 2 pi by r into r cube divided by g. Or we know that this r is equal to r plus h, where r is the radius of the earth and h is the altitude. So t is equal to 2 pi by r into root of r plus h whole cube divided by g. Solving this g is equal to gm by r square. Now the mass of the earth is equal to product of its volume and density. We know that it has got the radius of r, so taking the earth as a perfect sphere, its volume is equal to 4 by 3 pi r cube, so that equals to g by r square into m being 4 by 3 pi r cube into rho. Now r square and 3 goes, so g is equal to g into 4 by 3 pi r into rho. Putting the value of g here, we get time period is equal to 2 pi by r into root of r plus h whole cube divided by g 4 by 3 pi r into rho. Solving it further, taking 2 pi by r into the root, that t gives us root of 4 pi square divided by r square into r plus h whole cube into 3 divided by 4 pi into g to r into rho. Now 4 and 4 goes, 1 pi and pi goes. Further, it gives time period equal to 3 pi into r plus h whole cube divided by g r cube into rho. If we assume that the satellite is orbiting close to the surface of the earth, that means we can neglect the h. If h is less than, or in that case time period will be equal to root of 3 pi into r cube divided by g r cube into rho. R cube and r cube go, so time period is equal to 3 pi by g rho. It is the time period of the satellite that is orbiting close to the surface of the earth. As discussed earlier, t is equal to 2 pi by r into root of r cube divided by g. Putting the value of r equal to r plus h, capital R plus h, that gives us 2 pi by r into r plus h whole cube divided by g. Now if h is less than r, so h can be neglected here. That gives us t is equal to 2 pi by r root of r cube divided by g. Taking the r into the root, it becomes r square, that is equal to 2 pi root of r cube divided by r square g. R square and cube cuts out, that means t is equal 2 pi root of r divided by g. Now when the values are put here, giving r is equal to 6400 kilometers and g is equal to 9.8 meters per second square, the time period of a satellite that is orbiting close to the surface of the earth comes out to be 84.6 minutes. So it is the time period of a satellite that is orbiting close to the surface of the earth, and that is equal to 84.6 minutes. That means it takes 84.6 minutes, less than an hour and a half, to complete one revolution around the earth, but when it is close to the surface of the earth. Thank you.